Welcome to this short video on architecting for Azure with the focus on availability. My name is Vishwas Lele, and I'm going to be talking about why it is important to think about availability when moving your applications to the cloud, or perhaps you're building a cloud native application. So let us get started. As you know, that the cloud debate is largely over. Most companies, whether they're commercial enterprises or government agencies, are thinking about moving their applications to the cloud. However, through this talk of 4 nines and 5 nines and utility billing, customers have come to expect utility grade availability. So they expect that their applications, just by virtue of moving to the cloud, will have the same reliability as a utility service. And this has some challenges, not because cloud is inherently unreliable. In fact, when we started talking about public cloud many years ago, we used to emphasize on commodity hardware. Since then, we have come a long way. And if you look at Azure, for example, we have started out with 5,000 IOPS. We now have premium storage, 50,000 IOPS. We have the ability to get dedicated DTUs. We have a dual channel never express routes. So certainly we've done a lot to improve the reliability. However, when you're talking about a cloud application which has multiple moving parts, you inherently introduce the chances of failure. So how do you introduce these chances of failure? Well, even if the individual application or a component that you're using has 4 nines of SLA, if you put them all together, your SLA actually goes down because your SLA is a summation of all of these. So you're probably wondering to yourself that if the cloud is going to be not as reliable as my on-premises applications, why should I move to the cloud? Well, the primary reason for moving to the cloud is that you want to take advantage of the faster time to value. So you want the agility, you want the flexibility, and you want to release your software quickly. And in doing so, you are making a trade-off. You're taking advantage of all of these building blocks or the past building blocks that are available to you, so that you can reduce the amount of code or the infrastructure code that you write. But at the same time, the trade-off is that you're dependent on these multiple moving parts, and you also are dependent somewhat on the multi-tenancy and things like that. So how do you make this trade-off work for you well? How do you ensure that this trade-off is optimal to your needs? Well, you still want to continue to leverage these building blocks, but you have to think explicitly about failure, and you have to explicitly think about recovering from this failure. So if you do that, and this is really the focus of the talk, if you do that, you can explicitly recover from failure. Then you have sort of the advantages of both. You get all of these building blocks, but then you have explicitly designed for failure, so you can get the benefits of both. So let's talk about how do you sort of embrace failure, how do you focus on recovery. And it turns out that Microsoft has defined a methodology called the Resilience Modeling and Analysis, or RMA, and there's a link at the bottom that you can look at. You can download that link. You've got some papers and some artifacts. But the fundamental idea here is that you're addressing reliability issues early in the design, much like you do in a secure development lifecycle. You think of security up front. The idea here is to think about reliability up front and then prioritize availability and reliability related work up front. So how do you go about doing that? Here's an example, and the RMA methodology calls this a component interaction diagram. And if you look at this diagram is not different from other UML diagrams that you probably use for your architecture and design. You have object diagrams, you have class diagrams. And if you look at this diagram here, typically your failures are going to happen at your edges of these individual components. So it's important to model the interaction between these components. So if you look at this diagram, there are some availability related attributes that have been added to this diagram. So let me point out a few of them. So you have a yield sign here, which represents that this component can actually throttle you under load. Similarly, you see here that the upgrade domains and fault domains are listed explicitly, so you can reason about them. You can also see certificates, which are often a reason for failure. In fact, they're color-coded, so you know what are the different sets of certificates. And then you have explicit SLAs for each component listed here. That's important. You can also see the number of instances that are running. So you can see the number of instances, in this case is 3, for example. And then equally importantly, you have an external interaction here, and you have the SLA for that external service listed here as well. So now that you have that diagram modeled with reliability or availability in mind, and you have modeled each of nodes, and then you have modeled each of these interactions, you can then go about and start thinking about what happens if any of these nodes fails. So in order to explain this concept further, what I have done here is I've started out with an application. This is my current architecture of the application. Let me just describe this architecture. And this was somewhat advanced. I just didn't want to use a very simple architecture so that I'm able to call out some of the important components. So I have the web app tier here. What is interesting is it is hosted in something called the app service environment, which you may know. It is the app service, but it is hosted in a dedicated cluster, which is then part of your virtual network. So it is directly linked to your virtual network. So you get network isolation. So this is your web app. Then we have a Redis cache instance right here. And then we have a virtual machine, perhaps. And then, of course, then you see this dotted line here. That's because all of the services that we talked about up until now are directly connected to your VNet, or in other words, private peered. But then you also have some public peered services like storage. You have the Azure SQL database, and you have service bus. So this is your application right here, a web app, along with some VM doing some custom bad jobs, perhaps, a Redis cache, and then you have public peered services, storage, Azure SQL database, and service bus. So if you look at this architecture, how would you go about thinking about availability? So let's start out with the most interesting edge, which is somebody calling this application from outside. And what if this entire region, so this entire region or your specific set of clusters become unavailable? So what if this goes down? Okay. So the obvious answer is maybe what we should do is we should take a copy of this application and then stamp it out to another Azure data center, which is, let's say 400 miles away. And if we do that, that's fine. But how do we make sure that the traffic is indeed routed across these two regions in a seamless manner? And as it turns out, that there is a service in Azure called the Azure Traffic Manager that you may have heard about. And you can seamlessly route traffic across these Azure regions. And the way it works is quite simple. It has built-in endpoint monitoring. So it will, every 30 seconds, it's going to monitor that web app in both data centers. And if there are 4 unsuccessful attempts, it will then redirect traffic to the other region. And then what is nice is that these health checks continue. So if the first region that went down came back up again, Traffic Manager will take a note of that and then continue to send traffic to it. So you're probably wondering, well, that's fine, but where is this Azure Traffic Manager running? What if that in itself is not available? And it turns out that the Azure Traffic Manager is a global service, so it's not a regional service. It's not pinned to a certain region, and it comes with an SLA of 4 nines. So if you take this Azure Traffic Manager into consideration, then our architecture looks something like this. And remember that the edge that we had cut out earlier, now we have this ability to send data or the traffic to other region. So if something goes wrong here, our traffic will start flowing to this region here. So we have solved the first problem. So we have modeled our availability. We thought of the first edge, and then we modeled it. But there are other edges in this diagram that we need to worry about. For example, look at this edge right here. What if the Azure SQL database goes down? And as you know, Azure SQL database comes with 3 copies. So you're paying for one, but there are 3 copies. So if the first copy goes down, they'll automatically bring up the second copy, and so on and so forth. But what if the Azure SQL database itself is down and your specific database is down? How do you handle that? So turns out that there is something called the Azure SQL Database Active Geo-Replication. And I'll show this to you in a moment. And the idea here is that you simply enable this replication across a secondary. You can have a number, I think you can have 4 secondaries, and your data is asynchronously replicated to this other secondary. And then you have this ability to fail over, so you can detect that you have failed over to another region, or you can detect that your database is unavailable. Perhaps you're monitoring that database, and once that happens, through some script, you can cause a failover operation and have your application start talking to a secondary. And you might take a latency hit, but that's fine. It is better to degrade your application rather than not have the application available. And I just wanted to point something interesting. Of course, keep in mind that you're replicating to perhaps another region, so there's some latency involved. And you can, if you wanted to take, if you're concerned about making sure that the data is available in both regions, you can call the stored procedure spwait database copy sync, which will cause you additional latency because it will wait for the data to synchronize in the other region. But if that's what you want, you can take advantage of that. So SQL Database Active Geo-Replication is a very useful feature. Of course, you have to think about what are your recovery time and recovery point objectives. You can, of course, even without the failover, you can go to a secondary and use it for a read-only operation as listed here. And then you have to think about the latency and where the secondary is located and what is the cost associated with that. So what I actually did was, just to allow us to delve a little bit deeper into this, is I actually created all of these resources in Azure. So let me just bring up the Azure portal here. And what I did was, remember the current architecture diagram that I showed you? There's a capability in Azure called the templates, where I have a template. Let's just bring this up here. And this is the demo that I was talking about. Let me just bring up this template. And you will see if I scroll further down, this is a big template. It is doing all of the things that we talked about. Spinning up the resources into data centers, the Azure Service Environment, the databases, the virtual network, the subnet, all of that is being done here. And this is the nice ARM template. All I come in here and I just simply hit deploy. And I can't show this to you right now because Azure Service Environment is a dedicated cluster in your environment, so it takes some amount of time to deploy it. So I went ahead and deployed it earlier. So as you can see, this is a rather large ARM template. And rather than actually scrolling through this and trying to figure out all the resources, I went back and actually drew this out for you. So let me just bring up my other dashboard here. So let's just go back here. Let me just pull up my other dashboard. And you will see in this dashboard here, when this refreshes, I'll come back to this in a moment. In fact, what we can do here is I can show this to you here. So this is what that ARM template is deploying essentially. So all of this is right here. Let me just go back to our original dashboard. And let me call out this resource group here, which has all of the interesting resources. Let's just drill down into that resource group. And let me expand this here. And notice here that this is a single resource group. And of course, as you know, the resource group can span across regions. So we have some VMs located in the West region. Then we have a VNet, a virtual network, which is in the West region and also the Central US region. And similarly, we have a database, and then we also have a replicated secondary database in the Central US region. So you can see all the resources here, and these came about by provisioning that template. Let's just drill into the database itself here. and this shows you all the properties of the database. I'm interested in the geo-replication feature here. And if I go into the geo-replication, I have only one secondary. And you can see here that our primary region is the central US region, which is online at this point of time. And then the secondary is the west region right here. Let me just show this to you. So this is the primary, this is online, and then this is the west region. And right now this is read only. And I can very quickly come in here and I can just say fail over from west US region to the central region. And you can see this is going to ask me to confirm this. And then this operation has been started, and within a few minutes you can come back and see that our central US region becomes the active region, and the west US region becomes the active region, and the central US region becomes the read-only region. So let's get back to the slides here. So this was the active geo-replication. So we have solved one other edge here. Let me keep going. So we have solved this problem. If this edge goes down, no problem. Our application can then talk to this database here, of course, assuming that we enable the failover. So let's talk about another node here. Let's just take the storage node, for example. What if this storage node went down, which means this cluster on which our storage is hosted is down for some reason? Maybe the table instance that we are using is down. What happens if that is indeed the case? Well, once again, storage gives you 3 copies, so you have local redundancy. But turns out that you also have option to turn on geo redundancy. So you have the local redundancy, but you also have something called the zone redundancy. And then, of course, you can turn on geo redundancy on a storage account. And then furthermore, you can also have the read access geo redundant, which means you can have access to a redundant copy in another data center, but in a read-only manner. And typically, the lag between sending the data from primary to secondary, in my observation, is 2 or 3 minutes. However, note that right now there is no SLA on this replication lag. However, you do get an API which tells you what was the last sync time. So if you had to make some decisions based on the last sync time, you can certainly do that. And there is a GitHub project called rtable, if you're interested. And what this library does is it synchronously writes to a table storage in one region and then writes to a second region. So if you had to fail over, you can be sure that this data is available in the second region. So you have some options available. You can take advantage of that. So once again, coming back to our diagram now, we solved the initial edge, of course. Then we talked about solving this edge failure, and then we talked about solving this edge failure. Now, in the previous diagram, I told you that I also have a VM. And typically, what you want to do is a single VM does not come with an SLA. So in order to get an SLA, I got 2 VMs, put them in an availability set, which means that my 2 VMs are in 2 different fault domains. So that's great. But one common problem that you may have seen is that even though my VMs are running in 2 different fault domains, they are backed by storage. They are backed by disks which belong to the same storage account. So if that storage account is unavailable for whatever reason, even though I have VMs in 2 different availabilities fault domains, my VMs can still be impacted. So how do I solve that problem? Well, turns out that I can certainly spread my disks across storage accounts, or I can take advantage of something called the VM scale sets, which is really nice because I can just quickly bring the instances up and down. And VM scale set also distributes my disks across multiple storage accounts. So it gives me that additional layer of redundancy. So moving on, so we have solved a number of different problems should any of these nodes go down. Let me also talk about one final example, our 5th example here, which is, let's say, the service bus example. So what if you are using service bus? Maybe you're using queues, you're using topics. And what if your namespace is temporarily unavailable? So this node goes down here, for example. So it turns out that what you wanted to do in this instance is you can have an additional namespace in the second region. And then you have two options here. You can have an active where when you're sending a message to the first namespace, you want to send a copy of that message to the second namespace. And then you can tag these messages for processing. That is the active configuration, and that has cost implications because you're keeping the two namespaces up. What you can also do is you can have a passive configuration where you are writing only to a single namespace, and if that namespace becomes temporarily unavailable, you can then start sending the data to a secondary namespace. Now this assumes that the logic, your business logic, is able to handle duplicate messages, because you can run into a situation where the same message, because of the lag, can arrive twice. So you may end up processing that message twice. So you want to make sure that you have some logic to handle duplicate messages. So with this, we come to the end of this session. And hopefully what you take away from this session is that public cloud offers a number of benefits. It offers a number of PaaS services. But then you can't just assume that just by moving to the cloud will give you all these benefits. You have to explicitly think about availability. And my advice is that think of availability up front. And as you're designing your application up front, think of availability, and then bake in how you can recover from these failures. And by doing that, you're sort of taking advantage of the public cloud capabilities, the agility, the time to value, at the same time buying yourself the resilience that you expect from your cloud-based applications. So hope you find this video helpful. Thank you for your time, and thank you for watching. If you have questions about this video, or you would like to continue this conversation, my Twitter handle is vlele, and I encourage you to reach out to me and talk to me about how you are dealing with availability challenges with the applications that you are building. Thank you for watching.